Section 3.5, complex zeros and the fundamental theorem of algebra. Just know that if you see the word fundamental, that's important. It's a big word. It tells us something's important. So the fundamental theorem of algebra part 1, as you can see, says that every polynomial that has a degree of greater than or equal to 1, so it could be linear, quadratic, cubic on up, has at least one zero among the complex numbers. So that can be real and imaginary. There is underneath that the complete factorization theorem. Every polynomial, same thing, degree n greater than or equal to 1, can be written as a product, the multiplication of linear factors. So linear factors are factors that have degree 1. So for example, you're seeing this polynomial here. Remember, we've talked before about how a doesn't change the actual zeros, but it has the aspect of changing like the shape of the polynomial, like stretch it out, does different things to it. But you can take a polynomial C and you're just writing it as a series of these factors that are being multiplied together. And all those C values that you're seeing are just some value among the complex numbers. So they might have real parts, imaginary parts, one of either, but you can do it. That's the point. You can do it. So a real easy example would be something like P of x equaling x cubed minus 2x squared plus x. If you would like, you could take a moment, see if you can factor that. We can pull out a greatest common factor. We see that we've got x squared minus 2x plus 1. Notice that we'd have to have minus minus. There's only one factor of 1. So we get this. So here is the product of linear factors. X times x minus 1 times x minus 1. Now technically that x in the front could be written as x minus 0. Not a real reason to write that, but you could to see it as that factor. It's x minus 0, so just x, times x minus 1 times another x minus 1. You might also write it if you wanted to, since it's x minus 1 times another x minus 1. Another way to write it would be like this. But the point is, it can be broken down. It's of degree 3. It can be broken down like this. For b over here, p of x equals x squared minus 4, you might be thinking, okay, can I factor that? Well, it's not a perfect square. It also is not the difference of squares. It is just x squared plus 4. So one thing to do to think about the zeros of this and how you could write it would be, since it just has one variable part and one constant part, you could think about what would happen if you were to set it equal to 0 to find the zeros. You're going to notice that you're going to end up with x squared equals negative 4. And, well, if you were to square root both sides, you're going to end up with plus or minus the square root of negative 4. Not good or bad, but hopefully it will tell you that you have values, these zeros are complex, basically. I'm just going to move myself over a little bit. So understanding that the square root of negative 4 is a 2i, because the square root of 4 is 2, but the square root of negative 1 is I, we end up with x is plus or minus 2i. Now, all that we're trying to say here with this complete factorization theorem coming down from the fundamental theorem is you can then write x squared plus 4 as the product of two factors. Both of those factors are going to start with x, because that's how you get your x squared, but then you're going to have these two zeros that we found. We end up with these values here, as you can see. So if you were to multiply this out, you're going to come back to x squared plus 4, but you do want to understand that the bottom version that I have here is the way that it is written with those complex numbers as linear factors. Okay. Now, you could have, like we've already seen, that x minus r, where r is the 0, raised to the power of m. So Just remember, we just saw an example where it was, this is that example from just right above you there. In the notes, x times x minus 1 squared. Understand that 1 in this case, which as you recognize is coming from this factor here, it is a 0. 1 is a 0 because it makes it 0, but it's of multiplicity 2. And that's just because there are 2 factors of x minus 1. So that's how we say it's multiplicity, however many you have that are multiplied together. So in this case, 2. Now, the second part of the fundamental theorem of algebra is saying you have a polynomial, its degree greater than or equal to 1, then it has exactly n complex zeros where you're counting each factor as 1, giving you 1, 0. So the point is here, if you have your polynomial x cubed minus 2x squared plus x, it has exactly 3 zeros. So n equals 3 because that's the highest degree. So it's going to have 3 zeros. And we already know that because we can see from our factorization here that we get 0 and then a 1 and then another 1 because we see that twice. So it's not like we're going to do anything with that extra 1, but we do want to understand that there are exactly 3 zeros. It's just one of them has multiplicity 2. Okay, so now we're asked to find the roots of the equation. That's the same as, the solutions to this equation, the values of x that make it true. We're being told that 3 is already a root. So by knowing that 3 is a root, now we could have used, understand, the rational zero theorem, the rational root theorem, which would have allowed us to, at the very least, give our options for the rational zeros, but we're being told that 3 is a root. So what that does is it allows us to take this thing, which is cubic, and it allows us to take out a linear factor of x minus 3. So if 3 is a root, x minus 3 is a factor of that left-hand side, meaning I should be able to write it as x minus 3 times some quadratic. So I'm going to put the 3 here, and then I'm going to use synthetic division to do this division to help me out. So you are welcome to go ahead. You can pause. You can do the synthetic division here. Make sure you get it right, and we'll go from there. So bring down the 1, multiply, add. Multiply, add, multiply, add. There we go. So what we've learned from this is that that left-hand side can be written as x minus 3 times x squared minus 4x minus 8 equals 0. So we pulled out this factor, not by factoring, but by using synthetic division. And now we're left with a linear factor and then a quadratic factor. But what this fundamental theorem says is we should be able to take that quadratic and write that as 2 linear factors, 2 binomials that are linear. Now, the issue with that, of course, is how do we find it? And you can try to factor this. You'll notice that 8 has the factors 1 and 8. 2 and 4. The difference, addition or subtraction of those pairs of factors aren't going to give us the 4 in the middle. So this does not look like something that we're going to be able to factor. So the next thing that I would do is I would take that quadratic and I would say, okay, so either x minus 3 equals 0 or x squared minus 4x minus 8 equals 0. This is going to allow me to then, I need to find this. Can't factor it. I'm going to go right to the quadratic formula. You could complete the square. It's up to you. I'll go with the quadratic formula. Negative b plus or minus the square root of b squared minus 4ac all over 2a, where a, b, and c are the coefficients and the constant of that quadratic. Then I'm going to keep going. Oh, and c was a negative 8, not a positive 8. So negative 8. Continuing to go, I'm going to have 4 plus or minus. It looks like I'll have 16 plus 32, which will give me a 48 divided by 2. And then I think, oh, maybe I can simplify. Okay, but hold on. Don't simplify yet. We want to think about simplifying first. My point is you can't simplify the 4 and the 2. Not yet. Not yet. You can only do that if there's that last factor, that square root of 48, has something that you can simplify. So if I have the square root of 48, I want to think about the fact that 48, you can think of the factors of 48. You're trying to think of the largest perfect square that is in 48. So multiple ways that students learn how to do that. 48 is like 1 times 48, 2 times 24, 3 times 16, 4 times 12. How much farther do I need to go? It has a lot of factors. 4 times 12, 6 times 8, and that's it. Okay, so in thinking about those, understand that the square root of 16 is your biggest perfect square. So 3 times 16. 16 is a perfect square, and 3 is not. So that really tells you you've done a good job there with that, finding that largest perfect square. So what that means is we can take the square root of 16. We got to leave the square root of 3, sorry, buddy. And then now we have a simplified version. Now, understand, we can simplify this. We have a factor of 2 that is in the 2 top pieces and the bottom piece. So it's here. We can take out a 2 here. We can take out a 2 here. So what that allows us to do is, I'm just going to write it over here. We have 2 plus or minus 2 square root 3. These are not complex because we don't have imaginary parts, but they are not rational. So we've got that square root of 3. That's an irrational number. So these are not real. So any of the work we've done with like understanding, like Descartes' rule is not going to, no, Descartes' rule would work here because of the idea of having real. The rational zero theorem isn't going to do anything for us on this piece because these are not rational numbers. But it does mean over here that we have x minus 3. And then now, even though it might look a little bit odd, we can take, because understand that that's 2 values, 2 plus 2 root 3, 2 minus 2 root 3. So I always need to think of my factors like this, x minus, x minus. And then we just put in those factors that we have. So even though that might seem a little bit weird here, we've got, I'm going to put a parenthesis so you can see I have 2 plus 2 root 3. And I have 2 minus 2 root 3. And although that might look a little bit like a lot, those are the 3 zeros placed into those linear factors x minus c, where c is among the complex numbers. So it can be rational, irrational, real, imaginary. You got a lot of options there. But that is how you can break that down. So what we have found, I was just showing you that that's how it can be written. The question is find the roots. So we have found the roots. The roots are, we've got our 3, we already knew that. And then we have 2 plus or minus 2 root 3. So those are the roots or zeros or solutions to this equation, however you want to slice it. A lot of different terminology we can use there. Okay, so understand that we've got a note here. In the quadratic formula, you know what the roots look like. There's the quadratic formula right there. They're basically now, what you're seeing from here to here is just rewriting b squared minus 4ac as d. So it's just taking b squared minus 4ac and calling that d. Then, because you're dividing by 2a, it splits it apart so that each piece is divided by 2a. And then, this is where you got to pay attention because a and b are being used differently. These are not the same a and b because now they're capitalized, so they're not the same. Now we have basically 2 pieces, a plus b. If d is negative, then you're taking the square root of a negative, which means that you have 2 complex roots, a plus or minus bi. Okay. what you want to understand is if you have one of these, a plus bi, you're going to have a minus bi. You're going to have a minus bi. So just understand that. I can't really underline it because it goes into my settings. So you're going to have both. You're going to have a plus bi, you're going to have a minus bi. That's what we know. And it makes sense because you're always going to have that with the quadratic formula, you're going to have plus or minus. So d is negative. Now you've got a complex root and you've got both positive and negative. Okay, so the whole point of this is saying that we're going to do an example. We have that 2 plus 3i is a root of this equation that we see here. Our job is to use that fact to rewrite x cubed plus x squared minus 7x plus 65 as a product of those linear factors. That is our job. You are welcome to do any of this that you want. You want to pause it, you want to try something, and then come back and see if you got it. That would be great. Otherwise, you can pause along the way once you kind of get the hang of it. It's up to you. So from the last note, if you are told that 2 plus 3i is a root, you have to know that 2 minus 3i is a root. That needs to be true because you're going to have that conjugate. That tells us that, oddly enough, x minus, so these are our factors, x minus, and then 2 plus 3i, and x minus 2 minus 3i. Those must be factors of our polynomial. Okay? They must be, because we have these roots. The roots create the factors. Now, if you were to take x minus 2 plus 3i and multiply that by x minus 2 minus 3i, if you want, you can try that, see what you get. It actually comes out to be pretty nice. If you multiply it out, you're going to have x squared minus 4x plus 13. And it kind of makes sense because if you were to do the quadratic formula on that, sometimes you get complex values. So it does come out to a quadratic with real number coefficients. Now, we know, so what we now know is that this quadratic is a quadratic factor of that left side of that equation. So we can understand that there should be one more factor that is linear, because we're now at x squared and our left-hand side is x cubed. So there's one more thing that we're looking for here. And the way to find that would be to do division. Now you might say, well, I would like to do synthetic division, please. I like it. And I would say, I understand. However, remember, synthetic division works when you're doing division by a linear factor, x minus r. We don't have that. We're going to be dividing our cube side, this cubic, by the quadratic. And so we have to do long stuff. But our remainder should be 0 because we should be finding a factor. And if we're finding a factor, then the remainder is 0. So be aware of that. So again, you can pause, see if you can get this answer here, and then come back and see how you do. So not surprisingly, x times x squared is going to give me x cubed. So x times x squared gives me x cubed. And then x times minus 4x is a minus 4x squared. And then x times 13 is a plus 13x. Then we subtract. Whew, okay. So we're going to have, I kind of want to, I don't know why, but I want to shorten that just a little bit. I don't want it over my 65. So just right there. Okay, I'm going to stop. Okay, so now x cubed minus x cubed, that's got to happen. X squared minus a negative 4x squared is going to be a 5x squared, or minus a minus 4x squared. And a negative 7x minus a 13x would be a minus 20x. Then we're going to bring down this 65. Now again, the remainder should be 0 if we're doing this right. So now we think, what times x squared would give me 5x squared. That's a positive 5. So we have this. And we've got 5x squared multiplying the 5 by the x squared, the 5 times the minus 4x, and the 5 times the 13. So not surprisingly, look at this, look at this. Here we are. And we see that we are taking something and we're subtracting the same thing every time. Boom, 0. So what we have found is that our last factor that is missing, linear factor, is x plus 5. Let's look back at our question. Write the left-hand side as a product of linear and quadratic factors with real coefficients. So I'm going to put my solution here, the answer here that we've got, which is we have one factor of x plus 5, and then we have our quadratic answer of x squared, because it says we can leave an answer as a quadratic factors. I'm talking about up here at the top. So I can leave this quadratic because these are all real coefficients. That's all we're being asked to do. So understand, our job wasn't to find the zeros necessarily or anything like that. Not that we didn't do that essentially, but our job is just to rewrite the left-hand side. So we have x plus 5 and then we have our quadratic, and we have done what they've asked us to do, and we are done. And that is section 3.0.